In this video, we're going to continue our work with trig graphing and how we can use those graphs with applications. So this first problem is a pretty common problem with Ferris wheels. So if we go ahead and we just read what's given to us, it talks about the radius of this Ferris wheel is 10 feet. So let's go ahead and label that. So in our picture, from the center out to any point on the circle is going to be 10 feet. So it tells us that, which also means up top here, from the center to that highest point is going to be another 10 feet. And true for any other point on the circle from the center. And then it says the wheel is 3 feet above the ground. So that part I already see in the picture as well. So this is 3 feet. The amount of time the Ferris wheel takes to complete one revolution is 100 seconds. That right there is important. That is our period. That's how long it takes to go completely around the circle. So this is actually the period, the length of one full cycle. When Evelyn gets on the Ferris wheel, she's exactly 3 feet above the ground. So all that is telling us is the starting point is actually right here, because when she gets on the Ferris wheel, she's getting on 3 feet above the ground. So this is actually where it's starting. Then 50 seconds after starting, so halfway through, because remember it takes 100 seconds to go fully around, she will be 23 feet above the ground. So if you think about what that means, it says at the peak of the Ferris wheel, but if you think about what it means, if it takes 100 seconds to go completely around, so if I'm kind of going in this direction here, halfway would be at this highest point, which they're saying is 23 feet above the ground. So this distance is 23 feet above the ground, which that makes perfect sense because we have 10 feet, 10 feet, and 3 feet. So then it says then 100 seconds after starting, she will be back at the starting position. So again, 50 seconds, she reaches the highest. 50 more seconds, she's back at the starting point. So our goal here is to write an equation using cosine to model this. So what we're going to kind of think about this as, it's kind of like a unit circle, right? So think about the unit circle and how each of those points on the unit circle really became part of the cosine curve. Same thing with sine. So that's really what we're going to do. We're going to use this Ferris wheel and kind of think about that as, you know, it's cyclic. It's going to keep going around and around, which really means it's going to produce a sine or cosine curve. So if we think about kind of how is this going to relate to that graph, well, what's interesting is we're starting down here at the bottom instead of normally when we start at 0 degrees or 0 radians to graph. So when we start here, what's going to happen is, let's kind of sketch a picture here. So I'm going to say, well, the starting point is at 3 feet. So 3 feet. So let's go, I'm going to make this kind of a real rough sketch just because I want you to kind of see the connection before we formally graph it. Normally you won't show this, but I just want it to be clear how I'm getting these points. So my starting point is right here. So here's the 3 feet. And then let's think about what happens. So we start, and we like really these 4 key points, or it's really 5 key points when I get back to the starting. So this point right here is important because that point, if you kind of think about drawing this axis in, or think about this as this line would really be the midline because you go up to the maximum and then you go down to the minimum from that line. So this is really representing our midline, and at those points on the midline, so at these 2 points, this would actually be 20 or 13 feet because we have 10 plus the 3. So this is a midline of y equals 13. So that means we go from, let me actually sketch the midline in here just so it's pictured. So here's my midline. So we went from the starting point to the midline. And then we go up to this maximum point, so that's 23 feet, so then it's there. And of course, there's all these in-between points. And then we end up back to the midline. And then we end up back at the starting point. Oops, I wanted that to be pink. So then I end up back here. So now if you actually connect these, see how you're getting the cosine curve? So that's why this picture turns into cosine. And if I keep going around and around, the pattern's just going to repeat and we're going to get cosine. So that's the connection I wanted to make. Now let's actually go and write the equation. So the A value, well, our amplitude here, so think about from the midline to the highest point. So the midline to this highest point is 10, or the midline to the lowest point is a distance of 10. So my amplitude is going to be 10, which happen to be the radius of the circle. And then that means when I go to do my A value here, we notice our equation, we had to go down first since we're starting down below. So since we're starting down below, we have a negative A when we go to actually write our equation. So I'm just going to go ahead and make that negative. Remember, amplitude's positive, but in this situation, our leading coefficient is going to be a negative, so I'm including the negative with the A. And then for the B value, well, the B value comes from the period, so if the period takes 100 seconds, which is what it tells us, that means the B value is always going to be 2 pi divided by the period. So this is going to reduce down to pi over 50. So there's my B value. So pi over 50. And then for C, well, C is just the midline. So we already know that just by visually looking at it. You could also look at, the distance between the maximum and the minimum. And then from there, you can figure out the midline. So the midline, I think about it very visually. I think is the easiest way to kind of come up with that. So that tells me that C is going to be 13. So now if I go to write my equation, f of x is going to be negative 10 cosine pi over 50 times x. Make sure you close that parenthesis and then plus the 13 at the end. So there's my equation. So now when I go to sketch this a little bit more formally and actually look at using the time interval, notice I never labeled an x-axis or anything. So now we can actually do that. So we already said the amplitude is 10. So the amplitude is actually the measured in height, right? So in this case it'd be feet. And then the period was 100 seconds. That was the length of one complete cycle. The midline we have as an equation, so that's going to be y equals 13. And in order to get our graph, we're going to need some labels on here. So we want to break our period up into 4 equal intervals so that we can get each of those important points around the Ferris wheel or around the circle. So I'm going to say 100 divided by 4, so we get 25. So we're going to go up in increments of 25 seconds. So remember, the x-axis is representing the time it takes, so this is going to be in seconds. So I'm going to go up by 25, and it looks like, going up 2 boxes here will fit nicely. So 25, 50, 75, and 100. And I did read this previously, but it is important to just point out one complete rotation is what I'm graphing. That's why I'm only graphing those 4 labels. And then for the y-axis, that's going to be our height in feet. So for this, I'm looking at, okay, well, I'm starting at, I have a midline of 13 and I have to go up and down 10 from that. So what I'm thinking is if we look at our picture here, we have to start, our minimum is going to be 3. And if we go up by 3s, I think that's going to work out nicely because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sections. So if we go up by 3, that'll actually work nice. So I'm going to go up by 3s. You just have to make sure you can get everything to fit is the main thing here. So I know that the highest point is going to be 23. So let's go ahead and graph it. So we start at, so let's kind of think, I'm going to zoom out here for a second. Think back to your picture here. So just to kind of see it again. So our starting point is at 3. So we start here at 3, a height of 3. After 25 seconds, we end up right here at the midline. So now we're back to the midline. So the midline's at 13. So I'm just kind of approximating that. And then I'm going to go ahead and actually draw a line through that for my midline so that when I graph the other point, it's consistent. This is my midline. And then I go up from there, I go up to the highest point, which is up at 23. So now we're halfway through our cycle, so we're at 50. So this is at 23, again, just kind of approximating that. Then we're back 75 seconds in, we're back to the midline. And then when we're all done, 100 seconds in, we're back at the starting position. So I'm trying to kind of color code these points so you can see where they come from. So now when I go ahead and connect this, so let me zoom in, I connect, and we get our cosine curve. And again, we could continue this pattern over and over. I'm going to label this f of x, but I don't need to because it said just one complete rotation. So that's it. So kind of interesting going from a Ferris wheel, thinking about it now as a cosine curve. So let's continue here. So we have a couple follow-up questions. So it says, to the nearest tenth of a foot, how high above the ground will Evelyn be after 43 seconds? So the first thing I do is I look at the graph. 43 seconds, this is an x value. So unfortunately, when I go to the graph, I can't really see where 43 is exactly. And since it says nearest tenth, that's kind of indicating, all right, you're going to need to use a calculator here to get a better value. It's not just an estimate. So what's important here when we graph this into our calculator, or when you're doing anything with trig and you're inserting radians, so I'm dealing with radians here, I have to make sure that my calculator is in radian mode. And this is only true if you're inputting something into a trig function. So if it's in radian mode, which when we're graphing, we're always going to be in radian mode, we want to make sure that we get our calculator into radian mode. So if you go to the home screen and then 5-2, that will allow you to change the angle into radian mode if it's not already there. So just make sure you get that into radian mode. And then there's a couple ways you can do this. One would be I could actually graph this equation, and then I could graph x equals 43 and find the intersection. That would work. I personally don't love graphing x equals lines into my calculator, so I think for this one, it would be easier just to plug the x value in. So what I'm thinking the easiest thing to do would be take your equation from up top there, and I'm going to plug 43 in for x. So I'm going to go ahead and just copy this down. So negative 10 cosine pi over 50, and I'm going to plug in 43 plus 13. Notice I close that parenthesis. All of that has to go together. You have to be in radian mode here because we're inserting something in radians. We've used 2 pi as our period for the in radians, 2 pi radians, and we're inserting it into a cosine function. So you have to be in radian mode, otherwise you will not get the same answer as me. So I just type all of that in, and I ended up with, when I round to the nearest tenth here, I ended up with 22.0. And this is feet because this gives us a y value, so that gives us a height. So that is it for that. The next one here is now asking us how many seconds, after how many seconds, so now we're trying to find the time, will she be 18 feet above the ground? So now they're giving us the y value. So for this one, what we really need to solve is when does our equation equal 18? So this is what we're trying to figure out. So when does the function f of x end up equaling 18? So for this, of course, I would try going to my graph. Unfortunately, we don't have a specific height of 18. We see it's happening in a couple places, here and here, but I don't know exactly what that value is. So what I need to do is I need to go into the calculator, and we really just care about after how many seconds. So initially, the first time around, I don't care about when it happens the second time, according to this question. So what we're going to do is we're going to graph y equals 18 and the f of x equals negative 10 cosine of pi over 50 x plus 13. You're going to graph it and then you're going to find the intersection. So graph and find intersection. So go ahead and pause the video, take a minute to actually work through that, to graph it and find the intersection, and then replay and let's get an answer and hopefully we'll agree. So once you've calculated this, hopefully you've actually taken the time to do that. I ended up getting x equals 33 and a third seconds because it was 33.333 repeating. So to be a little bit more accurate, I said 33 and 1/3 seconds is what it's going to take. So that's what I'm going to write as my answer. If you didn't get that, make sure you go back and you try it again, so that you can confirm that you know how to do this in the calculator. So I'm going to go ahead to the next page here. And on the next page, I have a graph that it's talking about a building's temperature. So it's varying with the time of day during the course of one day, as follows by this equation. The air conditioning operates when T is greater than or equal to 80 degrees Fahrenheit. Our goal here is to graph the function for our time being between 6 and 17 and determine to the nearest tenth of an hour the amount of time in one day that the air conditioning is on in the building. So what we need to do is we need to figure out, first of all, we need to graph it. Then we need to figure out, well, how long is it on in the building? Well, it's only on when the temperature is greater than or equal to 80. So that's going to be important because that's going to be how I'm going to be able to figure that out. So one thing, first of all, before we get into our graph here, is we have a domain restriction. It's telling us that it only wants us to graph between these points. So that means when I go to graph this, I'm going to make a table, and I'm going to use my table instead of how we graphed in the previous units, because what's going to happen, so let's just kind of go through and talk about the characteristics. The amplitude here is 8. We have the midline is the 78 at the end. So midline is going to be y equals 78. But then when you start talking about the period, well, the period in this one is just going to be 2 pi because the b value is 1. So 2 pi divided by 1 is just 2 pi. And then if you go and you try to figure out the labels based on that, well, 2 pi divided by 4 is going to give us pi over 2. That's not going to work. So pi over 2 radians is not going to work for this domain because we needed to know from 6 to 17. So that tells me, okay, scratch the labels. You're not going to use those, and instead you need to use your calculator because of the restricted domain. It's telling you what your x-axis has to be. So we're going to use our calculator. And remember, whenever we use our calculator, we must be in radian mode. Now, if before you struggled to get your calculator in radian mode, remember you can go to the home screen to change that. From there, you should start a new document. If you already have a graph open and you change the home setting to radian, but not the individual graph page, it won't change your graph page. You can go into the settings into the graph. It's like when you're in the graph and change that as well to radian mode. That would, be an option. You just have to go into the settings once you're in the actual graph. So make sure that you're in radian mode, otherwise you won't get the right values. And then what I'm going to do is I'm going to go ahead and make a long list of numbers here. So T is my input, capital T is the output. So I'm going to graph from 6 all the way to 17. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. And then I'm just going to copy these right from my calculator. So I have 85.7, 84, 76.8, 70.7, 71.3, 78, 84.8, 85.3, 79.1, 71.9, 70.3, and 75.8. So now the nice thing is I already have my graph drawn, or my scale's already there and everything. What I am going to make sure though is that I put, if you look at our domain restriction, 6, we're including that. T can equal 6, but T has to be less than 17. So when I graph 6, I'm going to have a solid point there. But when I graph the 17, I'm going to make sure I have an open circle there because you're not actually including the 17. T has to be less than 17. So then the other thing here to make note of is our interval over here. So we go from 60 to 70, um, which means that halfway in between is going to be 65. I'm going to do this for all of the labels here because I think it's going to help me when I go to plot all of those points. And now I can go ahead and plot. So you're just going to have to do your best to make it as accurate as possible. So 6, and then I'm going to go up to 85.7. 7 is 84. 76.8. So go ahead and just graph all these points on here, trying to make them as accurate as possible. And 14 we have is 79. 15 is 71. Almost 72. I'm going to move this up. So I'm trying to make these, with respect to each other, look as accurate as possible here. And then the last one, so 75.8. So you can kind of see if we were to connect these. Oops, my last one's supposed to be an open circle because we're not actually including it. 75.8. Let me make that a little bit bigger so it actually looks open. And then we can go ahead and connect, try to make it look as curved as possible. You know it should look like a cosine curve, so try to make it look that way. So there's my graph. So then we have our midline we know is y equals 78. So we could graph that if we wanted to. So this would be 77.5. So 78 would be somewhere in here. I don't know if we really need it in this picture, but we could definitely put it on here. And then we have our other equation. Let me go ahead and label it now that I have 2 on there. So this is going to be t equals 8 cosine t plus 78. And then from there, now we actually have to answer the question. So determine to the nearest tenth of an hour the amount of time in one day that the air conditioning is on in the building. So remember, it's on whenever the temperature is greater than or equal to 80. So basically, here's my 80. So it's on during this section. It's on during this section. And now what I have to actually find is what are those numbers that it's on during, because the orange points weren't points that I originally had plotted. This one was. So I know that this was at 6, but I don't know this point. So what we need to do is in the calculator, you're going to want to use this graph and also graph the line y equals 80 to be able to see these intersection points. So you want to see when does your find the intersection between y equals 80 and this graph. So this first one is going to be at 7.6 comma 80. This second one I have is 11.2 comma 80. And actually I have it as a little bit more accurate number, which I'll write below. And then this is going to be 13.9 comma 80, which again I have it as with more decimal places. So really when we look at our picture, so when is the temperature greater than or equal to 80 degrees? Well, it's from 6 So including 6, so from 6 to 7.60. And then it's also from this section here. So that's going to be from 11.248. Again, if you need to change the float on your calculator in the graph document, make sure you do that so that you get more digits. And then 11 or 13.884 is where it stops, or when it equals 80 again. So notice I use hard brackets because it equals, it's when it's t is greater than or equal to 80, so it's equal to 80 at those points. So to get those values, remember I'll just write this as a note, graph y equals 80 and find intersection. Because you have to know those exact values. You can't just use the graph to approximate. We're trying to get as accurate as possible here. So now I want to figure out, well, how long is this? So from 6 to 7.6, well, that's 1.6 hours. And then from 11.248 to 13.884, so subtract those, you get 2.636 hours. Add that together for a total of 4.2 hours. So that means for 4.2 hours, that's how long the air conditioning would be running. So the last question here, so that last one was kind of long. I feel like that was an old Regents question too, probably, a larger point value Regents question. This last one though is another scenario with talking about low tide and high tide. So on a summer day in Cape Cod, the depth of the water at a dock was 4 feet at low tide. And at high tide, 5 hours later, the height of the water rose to 14 feet. Write a cosine function. So it's telling us that we have to write a cosine function to model the height of the water X hours after the day began at midnight. So that's important. So for me, I'm visual. I have to see this in a picture. I can't start doing this without a picture. So the first thing I'm going to do, let's sketch a picture over here. So we're going to say the starting time here is at midnight. So that means this is at 12 a.m. That's the start of the day. Let's go back to the facts that it gave us. So it said 4 feet at low tide at 2 a.m. So at 2 a.m., the height was 4 feet. So I'm going to call this 4 feet. Again, this isn't going to be the most accurate, but just to get the information visually. And then 5 hours later, so 5 hours later, that's going to give us till 7 a.m. That's high tide. Oops, I meant to draw that a little straighter here. So high tide, now the height's at 14 feet. So now we're up here at 14. Again, I'm just kind of getting this down as a visual. So now we're up here. And since we're going from low tide to high tide, this is telling us that this is the maximum. That's the highest point. This is the minimum. This is the lowest point. So when we connect these, we're missing some in-between stuff. So this is kind of half of our cosine curve. It's half of a cycle is what's happening. To go from the minimum to the maximum, we're at half of a cycle. So that gives us some information right there. So let me actually go with that for a second. So if the min to the max took 5 hours, that means one cycle is going to equal 10 hours because min to max is half of a cycle. So that tells me the period of this is going to be 10 hours. So from there, I can get the b value of my cosine function. So that means b is going to be 2 pi divided by the period. So pi over 5. So that's good. So I have that. Now, if I think about my midline and amplitude, well, midline is going to be halfway between the max and the min. So the midline would have to be, so halfway between 4 and 14. Well, there's a difference of 10. So it would be 5 units from either. So that tells me the amplitude right there as well. So I kind of did that in my head, which I think is probably fine with you to just do that. Um, so we know that this distance here has to be 5, and this has to be 5. Let's put 5 feet. So I just did 14 minus 4 gives me 10. Divide that by 2, I got 5. So that means the midline is 5 units below the maximum, so at 9, or 5 units above the minimum. So regardless, you're going to get y equals 9 for your midline. So that's good. That gives us another piece of information. We said our amplitude is 5, so we know that. We know that we had to go down first, so that tells me that it's actually going to be a -5 for that A value. And then the only other interesting piece here is notice that this is not starting on the y-axis. Typically, if this is cosine, it should be starting down on the y-axis. So you might be thinking, well, why isn't it just a cosine curve, right? Because if you kind of imagine this continuing, it would look like a sine curve, right? Because sine would start on the midline. But since it says that we have to write this as a cosine function, we have to consider the shift that occurred, because normally cosine would have started right here, and it actually shifted. So what happened with this is it shifted right 2 hours to get from 12 a.m. to 2 a.m. So that means now we have to put a horizontal shift on there. So when we take all of this information, we write our cosine function, it's going to be y equals, so it's a -5 because we went down, cosine, the b value is pi over 5. Since there's a horizontal shift, the horizontal shift goes in parentheses. The b value, remember, goes in front. Since I'm going to the right, it's going to be x minus 2, and then the amplitude is +9. So there is our cosine function. So that is probably, that has a lot of information in it. If I were to write it as a sine curve, I wouldn't have had to do the shift. But because it said cosine, you had to do the horizontal shift. So that's it. So go ahead and try those homework problems after watching this video.